In the course of physics of solar energy conversion, we are going to see the basic structure of a solar cell. So we're going to present the basic elements of how to build a solar cell, what is the essential of the operation of the solar cell. It begins with a semiconductor, and basically it will have two states. Low and high energy states can be, for example, the valence band and the conduction band of a semiconductor. Now in the dark, this is in thermal equilibrium with the surrounding radiation. So there are basically two processes of thermal promotion of carriers and recombination, and this is totally in equilibrium. Now, when you shine additional light to the semiconductor, then there is going to be an enhanced rate of generation of carriers. So that here, for example, we generate a lot of electrons, and consequently, there is a separation of Fermi levels or the internal chemical potential of the carriers. This is an incipient voltage inside the semiconductor, but there's no way to extract it. This is something happening inside the semiconductor that has got an excess number of carriers by the conversions of photons to electronic carriers. So here the energy of the incoming radiation has been converted to excited electron hole pairs inside the semiconductor. Now comes the step of taking this energy of the excitation in the semiconductor to convert it to electricity that we can use freely outside. We need to generate a voltage, and to generate a voltage, we need contacts. So now the semiconductor has been supplemented with two selective contacts. And the selective contact means that the contact on the left is going to take electrons. And then this will be typically a metal. Then the Fermi level in the metal is going to follow the Fermi level that has been generated in the semiconductor by the action of light. So that here we will get a high Fermi level of electrons, and to the right we will get a Fermi level of the holes in equilibrium with the internal Fermi level, so that each contact is at equilibrium with the respective internal Fermi level, but the two are well separated because there is an internal chemical potential. So now, since we have a difference of Fermi levels in the metals, this is a voltage as we have defined it. This is a difference of electrochemical potential of electrons in the two contacts. So now the cell can provide a voltage, and this is now a solar cell. So here we insist in the structure of the selective contacts. So it means that one contact is going to extract one type of carrier with a low investment in a step of Fermi level, but the other contact is going to block these carriers, and vice versa. The right contact will extract holes, but the electron selective contact is going to reject the holes, so that this structure will give directionality to the current and voltage obtained in the solar cell. So this is the structure of a diode. In practice, for making a solar cell, we need the structure of the absorber that might contain other elements, and there are also the structure of the contacts. So this is very important to extract the current and the voltage. Here we have the contact of metal oxide electron selective contact, or electron transport layer is also called, to the halide perovskite. Now we can see that we have a good energy match for extracting electrons from the conduction band of the perovskite to the conduction band of the metal oxide. On the other hand, here there is the band gap of the metal oxide is quite large, so there is a rejection of holes on the valence band. They cannot enter the electron transport layer. Here is a hole transport layer. Similarly, it will take holes, but it will reject electrons. The idea of a selective contact is not only the external current collectors, the metal contact, but it can be extended to the elements that touch the solar cell absorber. Here in a dye-sensitized solar cell, the absorber is a molecular species that will be excited. Then the metal oxide nanostructure will extract electrons, and a redox electrolyte will communicate with the holes. So that the selective contacts in this case are most of the volume of the solar cell. In general, we have the absorber. When it is illuminated, it is producing an excitation, and then this takes the form of carriers that are extracted at two different energy levels and two different chemical potentials, and the difference of the Fermi levels and electrochemical potentials, this is the open circuit voltage of the solar cell. To produce electricity, there is not only voltage, there is also current. So we must analyze the flow of carriers. Let's start with the illuminated semiconductor. It has non-equilibrium populations of electrons and holes with an associated separations of Fermi levels. But these carriers will disappear by recombination if we have only the semiconductor. So that with time, the excess population will vanish and the semiconductor will return to equilibrium. So that this excess energy existing into the semiconductor in terms of the excitations disappears after a time related to the recombination lifetime. So here is the energy, and we want to try to use it to take advantage of it. So we provide another pathway to the carriers. And in this pathway, the carriers, instead of recombining inside, they go from the high to the low energy state, producing external work in some system that is interesting to us. So now we have the voltage, and the flow of carriers is the current, so that this is external power. There is still some internal recombination. This can never be avoided, but now the majority of recombination is taking place outside. Is the energy that we can use, so that we need to explore the concept of efficiency from the total energy of the incoming photons. How much energy can we convert into electricity that is used outside the solar cell? So this is another view of the process of the photoelectric solar energy conversion, in which we have the electron-hole pair. The carriers have the respective Fermi levels, and this is, even though the energy of a relaxed electron-hole pair is the band gap, the energy that it's going to produce outside is the voltage. And the carriers are extracted at the selective contacts, and the flow of carriers is going to produce a current, so that the current and voltage is going to give electrical power.